All right. Wow. Wow. Homework. I think I turned in homework turns in candy. Homework for candy. Homework for candy. Some of this might even be able to eat. I don't know how to read the ingredients, but if you use Google Translate, you might be able to figure out more. Oh, we did. Yes. Thank you. Homework for candy.
What homework?
Whatever homework you have to turn in. Yeah, you're late on homework.
Yeah. Oh.
If you're not late on homework, you get a bonus kid.
Well, it turned on my homework, but I gotta review it.
Go ahead.
Ongoing. Yay.
So these are like this gel thing. This is like a gel thing. I don't know what these are. This is like a chocolate thing. I don't know what these are. These are really good. They're like a jelly bean, but better.
Oh my god.
And I don't know what that is.
Oh, I've always wanted to try these.
How is can
Yeah.
better in every way.
Better in every way.
Every way.
Wow.
There's 40 million people who live there. In the population. What?
You personally counted?
Yeah, every single one. Took me the whole time. No, it was fascinating. You know, there's a large cultural difference, obviously.
Yeah.
I don't speak Japanese. But everyone's really kind. And the first day I was completely overwhelmed, but then I like worked with people who I know from other missions, and so they like showed me how to get around and everything else, and that was great. If you can get over the language barrier, everything about it's better. So imagine 40 million people, which is 4 times the population of LA, but it's a completely walkable city with these things called trains.
Yeah.
It's
Yeah.
fucking crazy, bro. There's no traffic on any of the streets. Like there's no graffiti anywhere. There doesn't seem to be any crime. It was wild. Food is really cheap. Best sushi I've ever had at a random convenience store.
Oh, shit.
Wild. And you guys know I care about food.
Yeah.
So, you know, that's what I went for. Science is second, you know? Science is second. Anyway, but the mission is great. Everyone there is really interesting. Science seems like it's gonna be fucking crazy. They're gonna land. Did I tell you about this mission? Like, okay, so the proposal, the reason that I am participating on this mission has to do with, I have an interest in planetary science, in particular looking at how the Martian moons. So one of the questions we have is like where the Martian moons come from. They're very small. They both orbit in the same direction. And I don't care about that. That's not something I care about. Well, I care about the atmosphere of Mars. They're gonna go study the moons themselves, and I'm gonna use their spacecraft for bonus science. So in particular, we're gonna look at the atmosphere of Mars, we're gonna look for clouds and things like this. But what they're gonna do is really cool. They're gonna go to the moon. They're gonna take a bunch of pictures of the moon. Then they're gonna land on the moon. They're gonna grab some of it. Then they're gonna go to the other moon and they're gonna grab some of it. And on the way there, coolest thing I've ever heard of, before they go to the first moon, they're gonna drop a rover that's gonna drive around on the surface. Now, one of the things that you have to remember, it's a very small moon. So small that if you drive too fast, you fly off the moon. So they're gonna be driving 1 millimeter per second. So I was asking, you know, how far do you think you'll get over the course of 3 years? And they're like, well, maybe 100 meters. It's like, okay, that's pretty cool. So they're gonna drive around, they're gonna try and like do some spectroscopy on the surface, they're gonna try to understand the composition. So this is a mission that will start, well, I guess starting now, obviously, they're building it. I'm not doing anything, I don't touch anything ever. And so the flight from Japan should be August of 2024, and then it'll arrive in September or August of 2026. And so if you're interested, there is summer funding available, I believe, starting next summer. If you know someone else who wants summer funding or maybe is interested in planetary science, let me know. And then maybe we can trick them into letting them go to Japan. And that won't be for any of you, because you'll hopefully all be graduated by then. But if you have a friend, you're like, you wanna go to Japan in 2 years? That's the person. Okay, thoughts, comments, concerns? I know you're upset. Reed currently works for me, he's like, what the fuck, man? Okay, you can have a bonus, Katie. Yeah, you'll graduate, it'll be fine. Keep failing the class. Okay, all right, how was everyone's break?
Really good. No homework.
Really good, you had a homework, it's due on Thursday.
Any problem?
Yeah, no.
It just isn't true. It just is.
No, I actually like look at the
No.
modules.
Someone went in and deleted it.
Oh, I did not. I did not.
Okay, all right, I'm gonna look, I'm pretty sure I assigned problem.
No, I actually looked at it last night.
It's a
You
10.
did that. No. There's no.
We're not messing.
Go in there and delete stuff.
You might be able to, I don't know if
That would
I
be
should.
pretty
I don't think so. If I could, I would have much sooner.
Every week.
I think you would know.
I'm gonna look in the revision history, we're gonna see who revised.
Oh, no.
Um,
Oh, no.
okay, that's interesting, so there's supposed to be a homework.
Yeah,
Okay.
radiation.
Yeah, it was supposed to be 10:14, I think,
Okay.
but I'll double check, as soon as we get out of here.
Before.
Okay, well, maybe just one problem then. Since that's less time than I thought I gave you. I thought I planned all the homework out, but maybe I just wrote it down on a piece of paper, because I do that. Some folks took the exam, so I haven't looked at them, I got them this morning. How'd that go for folks who took it?
Mostly good.
Okay.
Mostly.
Mostly good. Mostly good.
No, like who's a guest? Like.
Oh, Kalorian her kid.
Yeah.
Last 2 weeks ago.
What a guy.
Cool. You wanna just jump in? Do you have any questions before we get started? So there'll be no strike for us on this campus. There's 2 weeks of class. That's it. That's all I have for you.
What, did they actually like, there's no strike for us? Like, did they just like?
So it'll be,
Oh.
it's called a rolling strike, so
Oh.
every campus is gonna do 1 day of strike at a time.
Yeah.
Now, personally, I think that's silly. Yeah, I think you strike all at once for maximum impact and maximum disruption. You want everyone upset, right?
Yep.
Because people are upset, make a difference. There's a slight inconvenience and you don't go to class one day, what are you gonna, you're gonna call your mom, right? Your mom's not gonna call her state senator, right? So, that's not how I would do it, but I think that it's a negotiating strategy or a tactic. Because there are specific actions we can take, so we're demonstrating mobilization. We're gonna say, look, we'll shut this campus down, slight inconvenience. So give us what we want, and then if they still don't give us what you want, then you cause a major inconvenience, right? Maybe. So that's the strike update. What else is there? Yeah, we have 2 weeks of class.
Yep.
We have a party, I believe, for the
Yeah.
departments. Everyone knows about that already?
Yeah. December 7th.
December 7th, something like that.
You'll see flyers, same graduation party.
They have the date, I forget what it is, but I think it's next week,
December 7th on Thursday.
which is a,
At 4:00.
okay, and it'll either be at the observatory, if it's not too windy, or down here if it is.
Yes, but don't spread that word.
I didn't say anything.
Respectful, dude.
Respectfully, yeah.
Anything else? Hey.
Keep this recorded.
Yeah, it's always recorded pause.
I
I don't know if she's here. All right. So they know what they're missing out on, right?
Yeah.
Can't read that. All right. So what were we talking about? Does anyone remember? I know it's been like 6 or 7 months.
We're talking about,
We did the power thing.
yeah, we looked at,
Light powered thing for life, good.
yeah, the power of like, an alternating dipole of 2 charges.
Okay, good. And just let's think about the steps that we need in order to do stuff with light, right? There is like a couple different things that we wanted to determine. So starting at the very end, the idea of getting radiation to infinity means what in practice?
Not too many R's on the bottom.
Yeah,
Not too many R's on the bottom, and not how many.
we want one of the.
You want
You want it to be fonts.
You want something to be constant as it goes to infinity. So
So
let's go
power-
backwards, yeah, so P looks like,
You want?
that's right at this side.
Uh,
Energy over time.
oh,
It-
1/r
that's not
times
the-
1/r times.
That's how we want it to end up.
Yeah.
What am I multiplying? Gotta shake the cobwebs off. We gotta remember E over T, that's a great definition, but that's not what I'm asking.
Oh, 1/e plus,
It's, yeah,
What? Nope.
that's, yeah.
Are we
There's
using
gonna be-
the pointing vector?
Ah, what's the pointing vector mean?
That's energy.
that's not the.
Plus.
S dot dA. And what's here?
Integration.
There we go. Okay, so that's the power. Okay, and so then I heard that we want this thing to not go like larger than 1/r squared, because this thing tends to go like r squared.
Mhm,
And then if you multiply them by each other, then that equals a constant, right?
mhm.
Okay, so then this really is comprised of what, two pieces?
Yeah.
Very good. And to get these two, we need,
Varying current.
Yeah, well, I guess like.
good, so the I would be like way over here.
We need 1/r, is that what you're asking?
If I'm thinking, you're right, like, we want it to be of the form 1/r, but how do I get these functional forms? Where do I start?
It starts with like what thing we're looking at.
Yeah, how do I, if I'm thinking about, this is where I want to end up, power infinity, then I had to know what S was. In order to know what S was, I needed to know what E was. In order to know what E was, I need to know what,
Oh,
You're a V.
V
That's
is.
what you're.
Good, and then on the
and
side,
then the vector potential.
here. And this comes from, give you a hint,
The front.
Down.
Got it.
It's.
Oh, roll. Oh, right.
rho. What's rho?
Charge density.
Yeah.
Good. So what I see here is that if I know the distribution of charges, and I know the distribution of currents, and I say the I, maybe I should write that correctly. Yeah. Really good J, right? Okay. So if I know J's and I know rhos, then I should be able to get the power to infinity. And I can do this for anything. So far we have said for, some weird dipole that's rotating around in a circle. We looked at the distribution of how the charge was laid out. We looked at the consideration of the currents. We got the B fields and the E fields. We saw that they were related, and then we could figure out whether or not the thing radiated, right? So you can ask this question to any system. And you could ask this question of, say, current in a wire. Now you already know what the E and the B is there, right? Current in a wire. What does the B field go like? And how does it go with respect to R? How does it die off? 1/r, 1/r squared, over R squared, right? And what about the electric field? Also 1/r squared, right? So I already know that those things are radiated. Right? Wires aren't radiated.
Wires do not radiate?
Yeah.
Okay.
Not to infinity. They might radiate a little bit away.
Yeah.
Right? But it at infinity dies off. So this is how you could check any system. Right? Is this thing going to radiate to infinity? No. Okay. So that's the basic goal of what we're gonna try and do. I'm gonna talk about one specific system, which is gonna capture radiation. And then we'll talk about an arbitrary use, which will give you something really cool and a very fun German word. Like German word. No? Okay, that's rude. Yeah,
So we're off topic, so that means like these lights don't radiate to you, or
well, what is this like?
then just like a wire go, like, through like the filament?
There's no filament.
Oh, what's that?
That's I can't remember. the
Oh,
name
they're
of
the
it.
fucking tube lights.
Yeah, they're
Yeah.
tubes.
I don't know.
Okay, so fluorescent tubes
Fluorescent
do what?
Isn't it?
It's like, yeah,
Gas and electricity.
Yeah.
Yeah, they fluoresce.
I was
Yeah.
gonna say that,
So,
Nice.
so that seems like a dickhead definition, right? Like, oh, what does the light bulb do? It's lighting. No, that's not what I'm saying. So fluorescing is a physical phenomenon. So you're talking about a gas. And in fact, what you do in that gas is using an electrical current, you jump an electron up,
but.
right? And then when it falls back down,
It emits-
it emits light. That's fluorescence. Okay? And you can fluoresce in many different ways. Now, you might be thinking of a filamentary light bulb, the one that has a wire. You run a current through it, and it heats up and it emits light. You said, well, Mateo, you just said a wire doesn't emit light. But that is not what is doing the emitting. Why is that wire emitting light?
Heat.
Heat, right? And the heat is coming from collisional motions of the wire. So these things are literally moving, these chargers are physically moving and creating broad body, black body radiation. Okay, at a temperature of like 1,000 degrees Kelvin. That makes sense? So it's okay. So now we've understood two light bulb types. LEDs, you may what are LEDs? Do you know what those are? People in Astro 4000 should know this.
They're diodes.
And what do they do?
Somebody was like really clever about
I just, no, that's.
yeah, actually that might be right. Yeah.
Okay, so LEDs and CCDs are the inverse property of one another.
Yeah.
LEDs emit light from a diode and CCDs collect light, turning photons into electrons. And the other way of doing that is to take electrons from your wire and turn them into photons. Light emitting diodes. Okay. But that's all stuff that you get into in quantum, like second semester quantum. Okay. But the type of light we're gonna learn about is what happens when an electron comes to a stop. What? Yeah, red light electrons is what we'll learn about next, and that's called well, not first thing what we'll learn about is antennae, and then we'll learn about stopping radiation or Bernstein. Okay. How do antenna work?
Alternating current and wire.
It's really straightforward, right? So in fact, that's exactly how wired antennae work. You have some long wire. This, that imagine this is attached to the bottom of your car. Right? Top of your car. The bottom is attached to the top. Yeah, you can have one going down, but it doesn't work as good. Okay. All right. And you might have some system like this, where you're considering some tiny piece in here, I.dl. Z. Just gonna set up the system really quick and we'll talk about it. This is something with the L, 0. Um, I need to be more careful with these, but see if I can do it right. So we've looked at dipoles, and in particular, we made some in the last one, we made some assumptions about the relative scale of the wave number. We talked about how that is like a representation of the wavelength of the disturbance compared to the physical size of the dipole. And as we were working on the project, we were shrinking it down, that the waves coming off of it were much farther or much larger than the ones that we were considering, right? For dipoles, the dimensions of the system is small compared to the wavelength radiated. Okay. So if we imagine that this is to scale, right, that's pretty good antenna on the size of your car. What kind of light might this be sensitive to? Okay, is that smaller or bigger than this?
You're saying the light, we're trying to see if the light is bigger or smaller. Dependent on the thickness of maybe like the.
What was the question?
Okay, so the question was, in the past, we were looking at dipoles. Okay, and we were saying some small change in the dipole produced light, right? And that light had a characteristic wavelength. And we're talking about how we made some assumptions about it being far enough away, shrink down the size, call them relative to one another. We made all these assumptions. But one thing that we found out was that the relative size of the light is comparable to the dipole in the system. In particular, I said that it's small.
Light is smaller than light.
The thing that is creating it, right? So if you think about it this way, you have some, let's say, dipole moving around in a circle like this, and there is some perturbation, right? You're generating the wavelength from the motion itself. The light comes off of it as a specific wavelength. How would that thing generate something larger than itself? The answer is it could, not easily, right? And similarly, when I look at a wave or a front that might interact with this antenna, let's say that this is attached to my car. Let's imagine a really long wavelength. As it passes by and interacts with this object, this whole thing is not going to experience the full amplitude, right? Because they're really not going to see it. Whereas it might be much more sensitive to smaller wavelengths. Because if, for example, you have something that is maybe a half wavelength, right? Now it's going to modulate all of the electrons on this half, right? Up and down. And the whole thing is going to respond quite well, right? As opposed to being bathed in an entire wall, right? If the wavelength's too large, the whole thing is going to feel one impulse at a time, right? What you want is a time varying impulse in the antenna. Okay, conceptual? Okay. So, from before, what we had was you had some current going up and down the wire, right? And that was drawing out the radiation, it's creating it. What we're going to do now is we're going to imagine this is the time reversed. And we're going to imagine that this thing has some charge in here, or maybe it has some ability to be charged or have currents sent through it. And then we're going to let waves pass by it, right? And what is that going to do? That's going to generate currents that we can read out on the other side. Imagine there's a wire here that's going to our radio. Okay. So previously we had something like this. And we found that if you want to do this, generally speaking, you can always find it here at the midpoint and then multiply by 2. So you can find this value. Right? And you can do that. That's a fun little trick for integrals. You don't have to integrate the whole length. You just integrate on one side and you multiply by 2. That's only true if the situation is symmetric. We want to make sure that there's symmetry on both sides. Okay. Okay. So let's imagine a straight conductor of length 2L. Oops. So the whole thing's 2L. There's an oscillating current that's maintained by an external power source. Okay. Now we're going to visualize a series of current elements, I dz, or maybe I'll put it like, yeah, let's just I dz, moving up and down. Okay, and that's a lot. So let's find the field at some point, of arbitrary point P here. And we're gonna notice that these okay, each element is producing an electric field here, right? And the total E field is the sum of all of the E fields. That's reasonable. Each element, each individual element here, I, is gonna produce an E field here. And the total E field is just adding them all up.
Yeah.
Okay. So you're gonna end up with something that looks like this. E, we're not gonna solve this ourselves, you could if you wanted to. Want to solve this for all? Oh, no thanks. I appreciate it. So it could look like that. And this would be a format that you've seen before. You've grown to know and love it. Excuse me. You want the style answer? Okay. So you have a time varying piece. It's from your driven oscillator. You have your electric dipole moment. How do we find this electric dipole moment? Okay, well, we can write P as P naught cosine omega t. That's going to be in the z hat direction. So as a current goes back and forth through here, that's behaving just like our version, which was rotating, but instead of going left, right, it's just going up and down. That's going up and down with some frequency omega. So I just wrote it. Okay. You can also use a complex potential if you really want to. P naught e to the minus I omega t. I have no problem with that. Both of those are good. And then this one would just be the real part of that. Right? So we love complex analysis. I'm realizing though many folks here haven't actually taken complex analysis because that's in math methods 2. I love when I'm like teaching something and I never see it before my whole life. So I just expect you to know. What? That's why I'm teaching? Well, yeah, but I should know that you don't know it. Now I'm, yeah, 3/4 of the way through this semester, 2 weeks away. All right. So we can also say, of course, that I is ddt of q. That's the definition. we could write this as minus I omega Q naught E minus I omega T. Then this would be something like some nominal current. Right, and then that would be the fluctuation of the current up and down. Is that reasonable? Okay. To get IDZ, that's reasonable as well. You just take I. CZ. Okay. That's gonna be I omega Q naught EZ. Okay. And this is your dipole distance. That's P naught. E to the I omega T to my side. Right. And so another way we can write this. I'll let you show yourself if you want, using both of those, is that P naught is I omega. That's I. What?
What does the P naught encapsulate? Right above it,
This P is here. This is what again?
that's the dipole.
Exactly. So this is the dipole. And then this is the nominal dipole value, right? So this is the dipole amplitude, maybe I'd call it. And by definition, that is the maximum charge of the times the maximum distance. Yeah. Did you have one? Okay. Oh boy, there's so much bigger. All right, we're just gonna go. All right. So we could say something along the lines of E is gonna be minus mu naught I omega I prime Z prime. And these are the ones that we're gonna be integrating over when we do the dE, the full integral. And sine oh boy. A lot to come back to. I like vacation better. All right. So you could use the law of cosines here. In fact, you'll want to use the law of cosines to put R into the framework that we have seen before, which is in terms of this original R, this one. Right, so you can relate these angles with these lengths, so you can have them arbitrarily. Okay. So, do you remember the law of cosines? Want to see it? You love law of cosines? Everyone's favorite, okay? This is I notice these are the different R's, right? So you can't simplify this by using things like lambda is much larger than 2L. But you can say that R, we have this distance, is far enough away, because we do want to see how this power radiates to infinity. So we can say something like R is much bigger than lambda. And two L is much less than R. Okay. Make it. And that should allow us to say that Z prime is much less than R. What does that do? Using this bottom part, think about this bottom. Think about that and then think about that. Yes.
Say that R prime is equal to R.
Ignore Z prime?
Z prime should swap.
C prime.
Just look at yeah, that's what I'm thinking. R prime is equal to one.
Yeah, we could just say that. It's so insignificant. You can just look at the first term.
If R prime equaled R, then there would be no point in writing this at all.
Oh, yeah, we still need that.
Might as well write.
Okay, so but can we drop the Z prime squared?
Z prime squared seems like a good one to drop, right?
Yeah.
Okay, but how do I drop every term with Z?
No, we
Just
can't
Z
drop
prime.
every term to zero, because we need.
But how are Z prime and Z different?
Yeah, I actually don't know where Z prime is on this side. Is it like the little like length difference if it like also doesn't count?
Oh,
It's right there.
No.
Right there, it's right there. Sorry, let's see. The prime, sorry. I should have been working. This has to do with this location.
Yeah.
So this moves up and down, that's gonna be the Z.
Okay,
So this one here, there's no the Z, that's different. I just forgot. Right.
okay.
What I'm trying to say is, do I just get rid of the Z here?
No,
No, good. So this term we say to ourselves, that's small, and small squared is bad.
yeah, but let's see, slightly small, but it's not this small.
Okay,
well, it's supposed to be a little bit rare.
Yeah, R is big compared to Z prime, so.
big compared to Z prime. Okay.
So wouldn't it just be like R prime is equal to the square root of R squared plus two R cos something like that? Like that?
So if we just get rid of this. Then we're not gonna have the right units.
Ah, that's true, because it's a length.
The Z and the R on one.
Yeah, big and small.
Big and small, okay, so this is a very good idea. Okay, so let's start by saying something like R prime is equal to R squared. We like that one, that one's the easy one. What about this? What about that? Right? I didn't have the right units, so this is why I put the Z back, yeah.
Is that supposed to be R prime?
Did
This
we,
one?
did we raise it to the 1/2 power?
Oh, the T in Spanish? Let's see if I can-
Is that R prime squared, or is it, What-
That's perfect.
So, okay, so here's the thing that I want to. Okay, I want to do this. Z prime over R, because I would like them to be in that fashion there, but in order to do that, I have to pull this guy out.
Oh, so just divide the whole thing by squared.
hmm,
And the reason that I want to do that is because then this thing is,
Wouldn't that be one over?
no, because there's an R squared here, wasn't there?
yeah, sorry.
And then this is square root.
Oh, yeah.
So when I looked at this piece here, it's like, well, I don't really know how this thing is going in terms of R. So I had the Z prime R, but I really want to have it in terms of Z over R. Because then when I look at this piece here, right, then I can make expansions of it perhaps. The first step is to just drop this, which we already said, and then I rewrote those two terms. Now I have this.
Wouldn't there be an R squared outside of the parentheses?
Square bracket.
Oh, square root.
Yeah.
We're doing it.
Okay, so now what's the trick?
Oh, yeah,
Say that for everyone?
that's correct.
Binomial expansion.
Binomial expansion. Why?
Because it's got the set up, and now you have like that.
It's one minus,
We can use Z prime is much smaller than R, it's like a starting point.
Mhm.
Yeah. So. I'm trying to think about how we could write it.
Well, I don't need you to actually follow, because I wrote it down already.
I don't think so much.
Well, no one said they wanted to do it at home, so.
Yeah.
Okay. Straightforward, right? Everyone would have guessed. I think I did right. Oh, it might be this place. Who's cancel, right? And V over R. R comes back in, yeah, okay, we're good. Yeah, we're good. I use the binomial expansion.
Yeah. We like approximated. What we have.
What's the binomial expansion? Generally,
It's like, 1 plus X. And then raised to the n power, yeah. And then your first term is 1. And then the other stuff is like factorial.
all right, you can look it up.
Okay, well,
All that way.
Yeah. So the reason that I want to put it in that format is because I know that if I can get into that format, I can use binomial expansion. And in particular, the thing I like about the binomial expansion is it's going to have increasing powers of X. Right? So for me, the thing that I like is that if I can get something into the format here, where Z over R,
another R.
which I already know is gonna be small, then increasing values of that small power, right? Small squared, small cubed, they're all gonna become more and more negligible. So if I can write this in a format with this, where this piece here represents 1 minus a small thing, then 1 minus a small thing squared is still going to be of order the small thing. Okay. This is a technique that you will use, well, maybe not all of them, but some of you will use for the rest of grad school. If you're not going to grad school, you're like, fuck, I'm doing this for. Okay. So, see if I write this now. Okay, so this piece over here, DE looks like 1 over R. And 1 over R prime basically looks like 1 over R. So we're chilling. Okay. You have to be a little careful in the exponent. There's another R up here. So the last assumption would be that R is much, much bigger than oops, R, but that would be true. 2L, and that's okay. I already said that up there. When you do that, let's see if I can. When you do that, you do your integral. Everything comes out something very nice. E is.
Yeah.
You, right? The cosines of the cos. Perception, all right, okay. So generally speaking, for an antenna like this, you're driving some varying current through it. We don't particularly care about the specifics as we care about what we call the power pattern. And what this means is that you're sensitive in certain directions. Okay. One thing that I eventually want to be able to do is, in Astro 4000, we use telescopes. And you have like a visible light thing and draw it in. But you maybe have never played with a radio telescope in your whole life. And they are very easy to build. So what you do to build a radio telescope is you build a big ass antenna. Okay, and you have a couple antenna and you put them into phase with one another. And because each one of them is sensitive to power in a specific direction, you can scan the sky and you can find out where your signals are coming from and you can make an image of the sky. So in particular, yeah, it's cool. So you can see that Jupiter is actually the brightest object in the sky in radio. It's brighter than the moon.
Where in this equation does like it indicate like the direction sensitive?
Exactly. So this is exactly the motivation that I wanted. Thank you for my planted question as usual. So what we want to look at here is we want to look at the specifics of S, right? So before the stuff that I deleted, we wanted P at infinity. And we're really curious, like how does it depend on theta, right? That's your question. Okay. So in particular, we're going to write something like S is going to be 1/2 mu, the real part of E cross with B, more or less. Something like that. Okay, and that's really going to end up looking like E squared over 2 mu naught C in the R hat direction. Like that. This is going to go out radially away from the antenna. Okay. And if you now look at this piece here, the time average piece, that's fine. The time average is going to make that disappear, probably go to a half, thing similar to that. Okay. And instead, we're going to be looking at the rest of these terms. So if I square the rest of these terms, everything in here gets squared, everything in here gets squared. And suddenly my angle dependence becomes a little bit more obvious. Which are the angle terms?
The sine theta in the denominator is like the cosine or the cosine theta inside the cosine.
Right, so my angle dependent terms are double cosine squared 5/2 cosine theta, and I don't distribute the cosine on the inside as much as I want to, over sine squared. Cool, right? You have an intuitive feel for what that looks like? No. Good, no one should. So instead, take 2 seconds and figure out what it looks like. Write it down. I want everyone's best picture of the power diagram. Okay. Your hint is. Okay. It should be on a 2D coordinate grid like this. You're welcome to use anything that you have at your available.
Look it up.
We can't use a tangent here because of the.
Yeah, the difference in fucking,
There's a cosine and a cosine. So the cosine actually and the cosine squared.
This one is
Yeah.
Desmos?
What?
Desmos?
I said you can use anything that you have at your availability.
Well, I think it's.
I got it.
Google it.
Yeah, kind of. Wait, this one. I have white out. Why is it?
Did she use whiteout properly?
So committed.
Not very well. This is-
Yeah.
That's what we.
What'd you get?
Like this. What?
A snowman?
It's not.
A snowman.
That's so stupid. Well, no. Did I occur? No, this is the 2000. I know.
So what would you even call
Yeah. You need it. You
I got something.
late.
that? Oh, yeah, so maybe.
That's
you're-
what I'm thinking.
Wait. Oh, wait. Wait, no, thank you. It's,
Reluctant.
Like, I can't see
Snowman.
Oh, yeah.
Oh, supposed to place this right here,
Back
you
when
guys?
it was
I think I misplaced my squares.
the
Yeah.
percent, it's-
Some of the-
percent.
You guys have dance.
I'm
moves.
trying
trying to
to get that now. Oh, wait. Yeah, please.
When did you guys read?
I got the same.
I'm
thing.
just trying to draw it.
So it doesn't
This is
fucking
from
matter.
the one.
There you go.
So we get.
Yeah, same idea. Or you-
No.
All right, what do we get?
Oh, you use the X, so it's along the X axis. I put the.
Aye.
Stop.
Not an acceptable way to turn.
Yeah.
So just
So
like a
it's
straight
oh,
line.
it's the same thing, but it's.
So a different way of asking this is we're thinking about, this is an angle, right? As we go up, theta goes from 0 to say pi over 2. So where is it maximum?
One.
I said from 0 to pi over 2.
Oh, wait.
So pi over 2.
Okay, so let's see if that's true. What's sine of pi over 2?
One.
Yeah,
Is it
yeah.
one?
Is 1? Are we sure about that?
Sine pi over 2.
Okay, so sine of pi over 2 is 1.
Yes.
And what happens to cosine at pi over 2?
Goes to 0.
And 0 over 1 is?
0.
So the power maximum couldn't possibly be at pi over 2.
Shit.
Because 0 over 1 is 0. So that's-
Hang on. Can't be pi.
Okay, so this has to be 0 here. Okay,
Yeah,
Okay, so we agree that has been.
yeah, for sure. Got it.
and what about in the direction of pi?
Direction of.
Pi, 0.
You get like undefined.
Undefined, and how is it undefining?
It's like it's 1.
There's something over 0?
Yeah, it's something over 0
Yeah.
squared.
So let's think about how it heads there. Yeah, right, it's probably going up, why?
Divided by small.
Divided by small, right? Remember that we're making sine squared smaller and smaller and smaller as it heads towards 0. So where's the maximum of the power function?
It's when you get close to the sign being zero.
Oh, okay.
Okay, so you have a large number way out here, you have a large number way out here. So how do these connect?
Sinusoidal.
No.
Yeah.
This is not even close to a sinusoid, right? This is all sorts of hibbity jib. That's not it either. Okay, what about pi over 4?
That might be helpful.
Someone calculate pi over 4 squared and someone else calculate cosine pi over 4.
Isn't it the same? I thought it was the same.
Yes.
Yeah, I think that might be it.
Times CMX.
The square root of 2 over 2,
Yeah,
so this would be a half. Good, and this would be square root of 2 over 2.
so
So, I don't know what that is. It's something, right? Yeah. Okay, so pi over 4 here, some value, something good. Okay. If I draw these gratuitously,
It's not eight, it's infinity.
you get this pattern. And you can check that at home. Check that at home, kids. Okay, so this is the dipole antenna power pattern, and this is what we care about.
How is it go negative if it's squared? Humble.
Because remember what work the function is here is a function of theta. So at every location in theta, we are doing the p. So this is not a p of x and y. Okay, this is p is a function of theta. So as I trace out, I'm gonna get a value at both negative pi over 2 and also positive pi over 2. Makes sense? Okay. There's a fun problem that make you do it. Make you do it for homework. It's a fun problem though. 1122. Let's talk about 1122. We'll use the ideas.
I thought it was the time that you were saying.
With
That would have been pretty
that
good.
would've been sick.
Okay.
It would have been some minutes earlier.
Had a dream that somehow we like we're already back on the other side of daylight savings time. And that was but it is jet lag.
When did you get back?
Sunday.
So it's like you were midnight, still there midnight?
So when I left on my plane, it was 7:30 on Sunday,
In the morning?
and then no, in the afternoon,
Oh, okay. So you went back in
In the
time.
after hours.
in the afternoon. And then I arrived, and it was before that.
It was
It's cool, right? I knew what happened already. No, I'm just kidding. And then I tried to stay up really late, so I got back at I think 1 o'clock, or I got back to my house at 1 o'clock. I was like, I have to stay awake. I went and I saw my friend's kids, and then it was like 6 o'clock. So I left, I went home, and I think I stayed up till 8. That was like good. And then I woke up again at 11:30 for like 4 hours. That was very annoying. The next day was a complete wash. But today I slept in kind of normally. So I woke up at a reasonable time. I'm pretty good with jet lag. The trick really is just stay up.
Don't go to sleep.
Yeah, you have to stay up as long as you can. It sucks and your whole schedule's thrown off, but if you fall into the habit of like staying awake when you were last awake, ugh, bad. Okay. So you thought you could distract me and I would forget about this problem, but I didn't. Okay, this is 1122 in your book. Okay. We haven't talked about these. In fact, I kind of brushed over this whole concept of magnetic dipoles, but this is another form of creating radiation. So you can have a magnetic dipole, which is different from an electric dipole, just like we saw electric polarization and magnetic polarization. We're going to imagine a magnetic dipole antenna, okay, with a radius b. Antenna has a height h above the ground. Okay, has some magnetization M. It emits some power P. Has a frequency that you're gonna find. The radius is B. Okay. Is that reasonable? Okay. So the question here is, where should the measurement be made to make sure that this antenna is emitting the right amount of power up to the specifications of the manufacturer? Okay, so the question that we're asking for is to find a formula for the intensity at ground level. Okay. And you're gonna wanna look for I versus the distance, right? But the intensity is as a function of distance. Yeah. And you're gonna imagine that you're on the ground. So it's emitting from here. Okay.
The base of that, is that a B?
Yeah, that's the big news.
That's the radius of the magnetic dipole.
Okay.
So we're not gonna do this problem in its entirety. I want you to think, for about 3 minutes here, how you would even begin to start this, and then I'm gonna give you the answer for I. So tell me how you would figure out the steps for everything up to I, and then we'll talk about it.
All the equations you just gave us, all the I's are current.
Yeah, the I's there are correct.
Okay, so
So we can't use the last example, but we can use some of the techniques of the last example. And here, I don't want to think about an integral, right? You won't think about an integral.
The one.
I want you to think about what you would need to get in order to get to I. And then I'm gonna just keep that. You see?
And then I to the current. Or I.
Intensity. Let me write it like
Yes.
this. Oh. I'm not here asking for the radiation at infinity. I'm asking for the power at a given distance on the ground. So my question is, I have some antenna, magnetic dipole antenna. It has some beam pattern, whatever. And you stand on the ground with your little machine that measures the intensity of the radio waves. You walk around,
So
you need to figure out if the pattern is correct while you walk on the ground.
do we still need that as a pointing vector then?
Ah.
We start with the-
Condition 3 is like.
Right. If we have.
That's what you're supposed to figure out.
Oh, okay. On the screen.
Yeah, okay. Then, no, it's just like an antenna.
Yeah.
We need to go from power to intensity. From power to intensity.
How's that?
No, those are gonna be the same for us. I is the definition of the average of the pointing vector.
I have definition of, yeah, right.
I love it. Do you want to use that? Yeah.
You are permitted.
Thank you. I'm gonna start with it.
Yeah.
Yeah.
then with this antenna, it just has an overall magnetic moment
Oh, yeah.
like upwards.
Into it, which
It's like, what is, or is that M for magnetization?
Yeah, M is your magnetic dipole moment.
I think we should know what-
Yeah, we need that primary.
I didn't really have to use it.
Yeah, I'm pretty sure it's actually dash, or like, both sides.
Yeah. But we could use that. 'Cause that's- to help find the question.
It's probably
Yeah, there we go.
Which one is it?
Well, it's just in the book, the question's about spring.
Yeah, it's also confused.
Oh.
So it's like a different number, but
All right, it might be, that might be,
In the fourth edition.
Well, it's the same
look
question.
at 24.
Yeah.
It's the same
okay.
question, but with a spring.
how is it?
It's
Oh.
basically hanging.
Would it help us
Oh,
if it was a
look at
string?
1124.
No, but usually, if I'm looking at, the third edition versus the fourth edition, they're usually one or two problems.
Yeah,
It's
okay.
not,
So check 24.
What about 1120?
I'm looking.
Do it right now.
Gently, gently.
I think it's-
Oh, 23, okay.
Oh, okay.
Yeah, see, they're just like,
Just kidding.
Oh, yeah.
you know, I just wanna keep you guys on your feet, you know, make sure that you're participating in the learning process. Okay.
Anyway, you're getting funky with it.
Kidding, Smokey.
Yeah.
I mean, that's
So both E and D should have like that time.
just hours of bad brain.
Yeah.
Okay.
Do you need H?
I don't think so.
You don't. Well, you need H at the very end when you wanna know how far away you are,
Mhm.
cause you're on the ground.
Oh, yeah. but the-
Okay, so what are our rough steps here?
So we need to get E and B.
Okay,
Nice.
and in particular, because we're looking at a magnetic dipole, which one do you wanna focus on? Probably B.
Yeah.
B seems reasonable, right? You have some magnetic magnetization. How would you treat that? Some dipole moment.
We're gonna find a way to like relate magnetic dipole moment to the.
Sure.
The radius of this antenna is B, right? So it's- Okay, so
It's a small one.
probably just,
Do we need the magnetic susceptibility thing? Like, that constant, if we throw it as B for some reason. Does that make little m?
Not exactly.
Okay,
I was gonna like think about what if we integrate over closed loop. Right, and it's dipole moment.
Okay, so remember that we did like this idea of integrals. So in the front of the book, if you look, you'll see that the A and the V are given by,
Oh, wait, they're given by.
Yeah, this P power, that's the big thing.
yeah, that's the power.
So what do you think equations give us in class?
Oh, wait, the phosphine of
Yeah.
A.
What did I say at the beginning of class?
Power equals the integral of closed surface as that G is.
Yeah, so this intensity here is the definition of the time average Poynting vector. So then I need here E and B.
Yeah.
And the question is, where does B come from?
Like A and B.
A and B. And we have functional forms for A and B.
Okay, okay.
And the thing that you're doing different here is that M is a time varying M. So just like before, when we had P, and then the P was changing in X and Y, rotating in R, you can do the same thing with your M. So M becomes M naught cosine omega T.
okay.
Right.
So then it's dependent on its omega.
It's gonna be dependent on omega, yeah. And that's why you take the time average.
Oh, but so the B field would be, M naught cosine omega T.
What's that?
The B field would just be M naught cosine omega T.
No, lots of other things too.
Okay, well, that's a component of it.
Yeah, the component of it, yeah, exactly. Okay, so you're gonna end up with, according to equation 1139, I think, but maybe not in textbook version 4, we'll double check that. So it should look like, this should look like mu naught m naught squared omega fourth 32, so of course it would, squared c cubed so just like the other dipoles, this is coming out radially. And it's gonna have some angular dependence here in the theta. You can ignore all of that. That's all just constants. This is the part that you care about. Right? And as you walk along on the surface, left and right, you're gonna find out what the value of the intensity is at every location. You're gonna compare it to what the specifications are. You're gonna say, oh, the telescope's in working order. Right? Putting out the right amount of power. I can contact my friends. Right? Okay, that's not the end of it. That's pretty close to the end of it, but this will let you get halfway through this problem. So we'll do, I think, 1123, whatever this problem is, and there's another one that I assigned earlier, 1014. I think it's 1014. I'm gonna double check both of those when I get back to my office. Next week we'll do, on Thursday, we'll do stopping radiation, Bremsstrahlung. And then we'll stop with radiation. And we'll do special relativity. I think that's what everyone cares about. And no one has ever learned anything in the last week before. Right? The true or not? I don't believe that anything has ever been.
Or check.
Or you can level simulate.
Yes. Is that okay?
What if he wasn't fine with that? Like,
You can do it before. And if you want to, you can do it the week before too, but I just want to give people an extra week to, because everything that you turn in has to be turned in by your check-in.
Okay.
okay,
And I won't be here that Friday.
Do we have a check-in for astronomy?
No, you just have a final project. Everything just turned into me. When I see you, you're writing it up. Questions, comments, concerns?
mostly concerned.
That's fair.